Complex numbers, de Moivres theorem. So de Moivre noticed something very interesting, that when we have a complex number in polar form, in other words, when it's written in the form of or cos theta plus I sine theta, and if we take this complex number and we raise it to a power, that in other words, if we take that complex number and we multiply it by itself a repeated number of times, well, de Moivre noticed that when we write it in polar form, it's the same as taking that complex number in polar form, and instead of multiplying out the brackets a repeated number of times, well, what he noticed was all we had to do was actually take the modulus and raise it to the power, and take the angle and multiply it by the power. And we can see this on page 20 in our maths tables. So if we see here in the middle, we have de Moivre's theorem. And we generally don't use this little bit here. That's irrelevant, okay, for us for leaving cert. So really we're only looking at this part here. And what we're going to do is we're going to use de Moivre's theorem to do three specific things. So the first thing that we're going to look at is we're going to raise it to a power. So in other words, raise a complex number to a power. The second thing is going to be trig. So we're going to be showing left-hand side equals right-hand side using de Moivre. And the third one then is finding the roots of a complex number. So we're going to focus on type 1 today, raising a complex number to a power. Okay, so with type 1 here, we're going to raise our complex number to a power. So we're going to use de Moivre's theorem to find minus the half minus root 3 over 2i to the power of 6. So obviously we could take that complex number and we could multiply it out by itself 6 times, which would be quite long and would probably lead to mistakes. You could even use binomial expansion to expand out your brackets. But here we're specifically asked to use de Moivre's theorem, right? So we have to make sure that we're using it, otherwise we wouldn't get our marks. So we're going to have a few steps here, and let's look at the first one. So our first step is that we're going to draw the Argand diagram. So this gives us a sense of what quadrant does the complex number lie in, and that's really, really important for helping identify the angle correctly. The second thing we want to do is find the modulus and find the argument of z, where the argument of z is basically the angle. In other words, we're looking for theta here. And we want to make sure that it's in the correct quadrant. So we'll always be looking at the reference angle and then apply the correct quadrant rule to find the angle for either the second, third or fourth quadrant, if it's not in the first. So the third step then is to make sure that we write our complex number in polar form. So you've just calculated or the modulus and you've just calculated theta, the angle. So to write it in polar form, it's or cos theta plus I sine theta. And note that the angle theta can either be in degrees or radians. So choose one, but you have to be able to read radians. So our last step then is to apply de Moivre's theorem. So in other words, we take that complex number in polar form, raise it to the power of n, which then by de Moivre's theorem means that we take the modulus and raise it to the power of n and multiply the angle by the power. So the question will either ask you then to write the answer in polar form or Cartesian form. So if it's in polar form, you must make sure you simplify, and if it's in Cartesian form, then you write it in the form of a plus bi. So polar form, or cos theta plus I sine theta, or Cartesian or rectangular form, z equals a plus bi. Okay, so let's have a look at this question. So we're going to have to, first of all, take minus the half minus root 3 over 2i, and step 1 says we must draw the Argand diagram. So we mark our real and our imaginary axis. We're going to go out minus the half, and we're going to go down root 3 over 2i. and we're going to draw our right angle triangle. We're going to mark in theta, which then allows me to mark in the opposite, the adjacent, the hypotenuse, and of course the hypotenuse is the modulus. So in other words, we can see that this complex number minus a half minus root 3 over 2i lies in the third quadrant. So our second step then is to look at the modulus and the angle. So we can see by Pythagoras, we can find the modulus. So in other words, our modulus of z is going to be the square root of minus a half squared plus minus root 3 over 2 squared. So remember, O is only ever the coefficient that's going in there. So our modulus is the square root of a squared plus b squared. So in other words, if the complex number is a plus bi, then it's the square root of the real part squared plus the imaginary part squared. So minus a half squared is a quarter, and minus root 3 over 2 squared is 3/4. So 1/4 plus 3/4 is simply 1, and the square root of 1 is 1. So we have our modulus, or equals 1. The argument then can be found by getting tan. So we can see we have the opposite over the adjacent. So we can say that tan theta is equal to root 3 over 2 divided by a half. So if I'm dividing by a fraction, I'll turn that upside down and multiply, which gives me root 3. So of course we get tan inverse of root 3. And tan inverse of root 3 is 60 degrees. Or if we're working in radians, that would be pi over 3. However, this is where we always have to be careful. That's our reference angle. And we have already established at the very top here that we're looking at the third quadrant. So we have to say, but third quadrant. So what's our rule for the third quadrant? Well, it's 180 plus theta. So therefore that means it's going to be 180 plus 60. So our argument of the complex number is 240 degrees. Or if we're dealing with radians, well, 60 goes into 244 times. Therefore 4 pi over 3s is the same as 240 degrees. So you're sticking with one or the other, so either degrees or radians. Now I'm going to write my answer in radians, because again, that's the one that students always kind of have difficulty with. So therefore I'm going to stick with radians for my example. But if you choose to work with degrees, that's perfectly acceptable too. So we've done step 1 and step 2 now, where we've gotten our argon diagram and our modulus. So if we go back to our steps, our next step, step 3, is to write the complex number now in polar form and then apply de Moivres' theorem. So we have polar form is basically where we're going to have or times cos theta plus I sine theta. So in other words, minus a half minus root 3 over 2i in Cartesian form can now be written in polar form, where the modulus was 1 times cos 4 pi over 3 plus I sine 4 pi over 3. Now for the purpose of this example, I'm going to keep 1 there. Obviously we don't need to write down 1 because 1 times anything is itself. But I want to make sure that you would see if the modulus was 2 or root 2 or 8 or something like that, you would see what we would be doing with de Moivres' theorem. So step 4 now is to apply de Moivres' theorem. So we have minus a half minus root 3 over 2i. And the question says we need to raise it to the power of 6. In other words, multiply it by itself 6 times. So that means I would take 1 times cos 4 pi over 3, I sine 4 pi over 3, our polar form of this complex number, and we would be raising that to the power of 6. So by de Moivres' theorem, I can then take the modulus and raise it to the power of 6 and take the angle and multiply it by 6. And now all I have to do is simplify that. So 1 to the power of 6 is just 1. Cos 6 times 4 pi over 3 is cos 8 pi. And sine 8 pi times I. So that would be my answer in polar form. But of course, we're going to write our answer in rectangular form. So you make sure that you have your calculator in radians. And if you've written down 6 times 240 degrees, then you'd make sure your calculator is in degrees. So if we put cos 8 pi into our calculator, we get 1. If we put sine 8 pi into our calculator, we get 0. So in other words, if I take minus a half minus root 3 over 2i, and I multiply it by itself 6 times, I end up with 1 plus 0i. Okay, so what you're going to do for me now is you're going to go to your textbooks, page 311, and you're going to do question 4, question 5, part 1, part 2, part 3, and part 4.